Have you ever tried making a 3D Gaussian splatting scene with a 360 camera and it just didn't work? That's because you're using the wrong camera. But NVIDIA fixed that this week with a brand new project that came out. And I have something special for you today. I sat down with Sanja Fidler, the head of the Toronto-based AI research lab at NVIDIA, and she's going to tell you everything that they did to solve the camera issue, shadows, and a bunch of different problems that you run into when you're creating a 3D Gaussian splatting scene, and how now none of those are a problem. And better yet, this is open sourced, so you don't have to worry about any sort of licensing, and it works on any GPU. It's incredible. So I'm going to stop talking, and I'm going to jump into this live interview that I captured at GTC last week, and you're going to learn all about 3D Gaussian Ray Tracing and 3D Gaussian Unscented Transforms. And at the end, we actually do speak a little bit about diffusion models and how we can extend 3D Gaussian splatting scenes to do way more as well. Well, let's get to that interview. And I'd first start out with Sanja. Can you just introduce yourself, what research you like to lead, and what gets you excited about that?
Yeah. So I'm Sanja. I started at NVIDIA in 2018. I guess Jetson wanted presence in Toronto, and he started this lab. He even came to Toronto to open this with us, which was awesome. And I basically joined the org that's doing Omniverse. I'm not sure whether you know Omniverse is really this platform for really fast and photoreal ray tracing and simulation. Then I end up thinking, what should I work on at NVIDIA? Mm-hmm. And I wanted to be aligned, obviously, where we landed. And we decided to work on 3D content creation at that time.
Okay.
It was like nothing was there, It was like baby steps, baby area. And it developed so quickly, right? And over the years, we really grown what we call now a spatial intelligence, which is not just 3D content, how I create content is one aspect of it, but I also need to simulate it, right? So physics, I need to be able to understand it, right? So that I can, put proper semantics on top of my world that I reconstruct, so I can simulate it properly. So it's, basically like a more comprehensive approach to 3D.
Yeah, there's a big gap from understanding 2D photos to interpreting it into a 3D world and how it interacts with each other. That's something that at my company, every point I work at, our vision is you're going to capture every point in the planet with imagery and then be able to spatially query things and ask questions about it. And I feel like there's been an explosion in research to get us there, but there's still a long ways to go, right? The hardware is now kind of catching up, but there's a lot to do there. So majority of my audience really knows what 3D Gaussian splatting is. They've seen me do tutorials and how to get started with it, but what you're doing, what your lab has been researching is 3D Gaussian Ray Tracing and 3D Gaussian Unscented Transform. Is that correct?
That's correct.
What is so for my audience, they're not super technical, but they are somewhat technical, and they would like to know, like, what's the difference with when they distill it down from just Gaussian splatting, what they've probably been playing with these platforms, and what you're researching and felt?
Yeah, so Gaussian splats obviously revolutionize how we capture, right, to make it immersive content. Now, it has all these great things, right? Super fast to render, and it has really high quality. It is limited in the sensors you can use to create, Gaussian splats, basically to do reconstruction. It assumes rasterization connected to a pinhole camera, which is, a very idealized camera. And really kind of what we want to do is support developers to use any kind of capture device. You can have wide lens cameras, this more distorted cameras, fisheye, rolling shutter, which is much cheaper camera, much more widely available, right? So instead of someone that wants to create a really high quality scene, then instead of them needing to buy a new camera that kind of conforms to what Gaussian splat needs, maybe we can change the algorithms, right? So that they support everyone. So that was kind of the thinking, right? How can we now support like a much wider set of cameras? And the other thing that's interesting, because really like Gaussian splats nerves, they go after immersive experiences, right? But as part of that is also editing. Like I actually do want to insert stuff into the scene, you know, like a glass or an object, you know, I want to make it, you know, whatever use case I have, right? A commercial or a present for someone I want to put in a box there, right?
Yeah.
So I need to be able to like do that in a realistic way, right? So having this kind of ray tracing effects where I can cast shadows, I can do reflections. All that wasn't possible with the Gaussian Splats, and we wanted to solve that in the same spirit.
Okay. So you said you can use these really wide distortion lenses. So I could take like the equal rectangular, you know, capture, and I could get that off of a 360 camera and not have to do anything. You ingest it into your project and output
it should
sensible,
be as easy as that.
which is amazing because, for example, I played with other versions of the similar, even Nerf you can get away with some more distortion, and I can use a fisheye lens, make a model of my kitchen and 50 photos, and then I use a pinhole camera and it's 500 photos to get the same scene. So that's, you know, for the viewers, that's a huge benefit that you can use these super wide lenses and get everything in one capture. How does that help for robotics then?
Yeah. A lot of the sensors in robotics are actually like that, right? So, for example, NVIDIA sensors are rolling shutter, all right? So it's not instantaneous capture, but just capture basically column by column. What else? Yeah, there's always distortion, right? So they have, especially for parking, right? Like you need to have this fisheye to capture a very wide space. So if we want to basically take, you know, environment or like footage captured by robotics, like autonomous vehicles, we need to be able to reconstruct based on off of those sensors, right?
And that makes sense because you could put a handful of cameras on a vehicle with, you know, these fisheye cameras versus if you really had to pull that off with a bunch of pinhole cameras, it would look like a car with a bunch of cameras on every angle you can see.
Yeah. You just want to be flexible, right? What camera you want to support it, right? That's basically how you...
So that was the inspiration, was lots of flexibility. And then with ray tracing, you get all those benefits. So what's the difference then between 3D Gaussian Ray Tracing came out first, and then you came out with, it looks like it was just built upon that. You came out with Unscented Transforms. What's the difference there? Because I read the two papers, they feel similar.
Yeah.
But for people who may have read both and may be confused, what was the upgrade, or is it completely just different?
It's actually an upgrade, I would say, right? I think 3D GOT would be the thing to use for reconstruction. And then if you wanted to do a ray tracing effect, you would use the GRT for ray tracing. So basically, like the first thing we wanted, right, is support this wide range of cameras. And instead of doing rasterization, we do ray tracing, meaning like you trace a ray, right, through a pixel, you intersect your Gaussians, and then you compute the color this way. The issue with that we have, it had all these nice properties. Right now we could do all the kind of different cameras, and we could add an object in, cast shadow, right? It had all the properties we wanted. The issue is that it was slower, right? It was about, I forgot the numbers, 3-4 times slower in training, and then 2 to 3 times slower in inference. So you kind of lost something with respect to the Gaussian Splats, right? So to convince someone to switch, obviously, you know, you need to have, you know, like something that people really want. Plus, because it was ray tracing based on NVIDIA optics, it was kind of bound to work on RTX GPUs, which, you know, maybe not everyone has, right? So we were really thinking, how can we take the benefits of what this tracing formulation had, but actually made it available with all the GPUs and kind of be as fast as the Gaussian formulation, the original Gaussian formulation.
Okay.
And that, you know, the GOT basically was born out of that.
Oh, so you're answering questions I was going to ask next, you know, about hardware. So I guess before I then ask that question, well, casting shadows, I know that's a big deal. As you know, I've talked to people in media entertainment, they want to use this for virtual production or making some animated world, and it's a quick way to build a world without having to build the world, you know, the traditional way as a 3D artist. So then you're saying that I could simulate lighting in a scene, and the actual scene would cast shadows itself onto an object I add in there, or just the objects I would add in. Let's say I added like some sort of mesh-based object in that scene.
Yeah. The object would now cast shadow on the environment. Like imagine I have a car that I add in, right? It would basically cast shadow on the road or,
Okay.
or whatever, right?
Yeah,
I mean, we make it look much more realistic.
Yeah, I've seen people do tricks to try to then simulate that afterwards, and then you're right, it ends up this world where they're spending lots of hours just to get a shadow to track an object and trick the people watching this scene. So interesting. So then would this hardware work on these smaller on-device sensors that we're seeing from NVIDIA, the like those Jetsons, and could you train it on something that small and perhaps as you're capturing? Or
yeah, I would think so.
You might have to wait, but it's not bound to have a workstation graphics card.
No, it should work with anything that 3D works, right?
Okay. So you could get away with just like a consumer RTX card even.
That's right.
Most of my followers have already. They're already using
for reconstruction, right? So basically, like the formulation unlocks different sensor types, right? Now, if we do want to have reflections, refractions, shadows, and so on, so if we want to do secondary light effects, then you need a GRT formulation that needs RTX. You see what I mean?
That makes sense.
So you basically, there's an add-on to 3DGS, but basically wider camera set, but you still need the other GPU if you want to do fancier effects.
Okay. And I mean, most of the people who are using this already kind of assumed I need some sort of RTX card or a very decent GPU. You're not running around with doing these on your iPhone. Okay, so then I had recently covered a paper that you were also on. It was the Diffix 3D Plus. I don't know if that's how you say it. And I noticed that diffusion models are now entering in the workflows. How do you see them playing a role in doing novel view synthesis? I want to create new views. I might not have supported images. It feels like diffusion was the logical step. But
yeah. I mean, the reconstruction is limited, right, to things you see, right? So as soon as you deviate, at some point you degrade in quality, right? So, I mean, the autonomous car example, if I want to do a lane change, it still kind of looks good. 2 lane changes, becomes bad. You see this like popping effect and, the Gaussian. So obviously that's not desirable, right? And then on the other hand, if you just take diffusion models, it generates beautiful images. Sometimes it hallucinates. You don't always get what you exactly want, right? So kind of the marrying the two in a very like controlled manner might be the first way to make, this kind of generative simulation to be controllable, because we're going to ground it in 3D, as well as help reconstruction basically have more outpainting capabilities, right? So that was really kind of the goal behind the fixes. You basically, we call it fixer, actually internally. When you deviate from, the original capture position, you essentially use a diffusion model and you guide it with like a bad rendering. So it kind of gets that like idea of what needs to do, and then it makes basically strain to make it look good. Right.
It's like I don't know, upsampling is the right word, or
generative enhancer in some way, and suddenly now I can go 6 meters. It still looks great, right?
That's amazing.
And that's like the first way of actually making sure that you don't hallucinate. You guide it really well, and it provides value. All right, and it's you can make it fast enough. In that paper, we use like an image model, not a video model yet, internal to be actually really fast and quite consistent across time already.
Yeah, notice the video models take much longer inference time or training time, and
we're gonna get there, but it's not today, I guess.
Well, it's newer, We've had more time on all these different models, and everything seems to get faster and higher quality at the same time. I don't know how, but they do. That's really interesting. So you're basically saying is, I capture a scene. Let's say I forgot to look to my left as I'm going down a corridor, and I end up not having a lot of good ground truth imagery. So you're basically saying I can then rotate the camera when I'm inferencing, and then be able to then generate much closer to reality images than I would have had. I'm not, I think of all the times I've gone out and shoot something and think, shoot, I forgot to capture
That's right.
Images. Well, now you have a way to kind of recover parts of the scene that you didn't have good imagery from.
That's right. If I was recording you now, right, I could actually move after I'm back at a hotel much more, right? Meters away, even though I forgot to kind of move there.
Great.
Yeah.
So now you're breaking everything I've told everyone in the past. It's say, hey, when you capture, you got to think you have to, later you can render near where you captured, but you can't get too far off. No, I'm going to say, just go for it. Now,
there's still a limit there.
Right, there is.
But like we are really like pushing that, you know, like the deviation possibility from the original capture position. So
yeah. All right. So then as we're getting closer to thinking of diffusion models, I've been playing a lot with Cosmos recently. Ever the day it came out, I was trying to get it to work, and it worked pretty easily. And do you see all of this field of study of, you know, taking images and doing view synthesis? How does that play a role in like Cosmos's future? Do they work together, or is it going to be kind of different stacks that work in parallel?
I think they should totally work together. That's probably going to be the first really grounded use of Cosmos, if it's 3D grounded, right? One way is Omniverse. You know, Omniverse kind of has this 3D simulations, all physics-based, and now you want to use Cosmos as condition on that, you know, information, and produce like a photoreal, you know, all this effect. You can prompt it with different weather or whatever. And you can do the same as, you know, with neural reconstruction. You either construct it and now have this 3D information, and I can guide Cosmos basically to really be grounded in that and now provide more diversity. Because otherwise, if you just prompt it with some text, you don't always get what you want, obviously, right? And sometimes the model hallucinates and so on. So I guess the question is, who's the user, right? If the human is prompting and they just want to get a good looking videos out, they can probably do that after a lot of trial and error. If I want to do this, if I want to use Cosmos for robotics or physical applications where I need to really trust that whatever comes out is, you know, conforms to reality, you know, physical reality, then I need to have a lot more guidance coming into Cosmos to build that trust, essentially. Whether Cosmos eventually is just going to become the world simulator, you know, I have no doubt, right? But there's still a little bit of mileage to go there.
I think there's a lot of misunderstanding when it came out, what it does, and also when it first came out, not everything was available. So a lot of the post-training tools are still, well, they might be released tomorrow for all I know, but you know, everything wasn't quite ready. The developers even said, we got the diffusion models out, the autoregressive models, have fun with it. Post-training is coming. That's where I see this fit in too, is maybe I only have 500 supporting photos inside a warehouse. Well, now I can use something like 3D GRT, or you could use your Diffix 3D Plus and get thousands more images for post-training. So now this Cosmos model has a much better understanding of what your scene looks like. So now when I'm saying, hey, robot, give me 10,000 simulations of this environment, it will know all of these different views and not have to make it up, right?
You tell it how the environment looks like. Now you can prompt it to be in a different weather condition or a different lighting condition.
Yeah, I'm excited for that future. And I think, again, everyone thinks of Cosmos as just NVIDIA's version of all these, you know, Sora and all these other open video models, and it's not that. So I think there's a lot of education about what it is, and I think NVIDIA will be pushing a lot more on top of Cosmos, making it more interactive, like you said, like more of a simulator. So I'm excited to see where that goes and watch your work and that work kind of intersect. It's exciting. So
yeah.
Well, anyways, it was a pleasure having you today, and hopefully my audience learned something. You know, if people want to follow your work, you know, how would they find it? Do you know?
Yeah, there's a website, I guess, or you just search Toronto AI NVIDIA.
Definitely. I will make sure I link it wherever this video is. I actually look at it. I notice you put all your research papers in there, and I also, as I've learned, that everyone who works on these papers tend to be very open. So you know, if you have questions, the community seems very vocal about answering them, because you want people to use it, right?
Yeah, and the code is going to be released this week. So for 3D GOT and GRT, you know, later this week is out.
Exciting. So by the time you watch this, the code will be out, and you can have fun and ask us questions, and I'm excited to get my hands on it.
Yeah, and send us feedback.
All right. Well, thank you.
Yeah, thank you.
Well, there you have it. Now you can use 360 camera, fisheye camera. You can get shadows, you can play around with depth of field, all these cool things when you use a ray tracer, and they even have a fast version of it with unscented transforms. And again, I'll link the code to the repository where you can start working with this today, and it's open source, so you don't have to worry about those licensing fees. Thanks for watching, and I'll see you in the next video.